So electrochemistry is a new chapter we're going to study today. Now, electrochemistry, what is electrochemistry? Electrochemistry is a branch of chemistry which is concerned with interconversion of chemical energy to electrical energy. So either chemical energy is converted to electrical energy or electrical energy is converted to chemical energy. Now, what is electric conduction? We all know electric current represents a charge transfer, and a charge transfer or flow of electricity occurs through a substance called conductors. So here in this substance material, you can see the electrons are flowing from negative to positive. Conductor. What are conductor? Conductors are the material through which the electric current can pass. They allow the passage of electric current. So they are normally metals. Metals which allow the pass of current is called conductor, and metals which do not allow the pass of current is called insulators. So copper, aluminium, steel, they are metals which are conductors. Now types of conduction. There is two types of conduction: metallic conduction or electronic conduction, electrolytic conduction or ionic conduction. So metallic conduction is a conduction which happens through flow of electron, while electrolytic conduction happens by flow of ions. Okay. So metallic conduction, flow of electrons present in the conduction band of metals under the influence of applied current allow the passage of electricity. And electrolytic conduction, charge transfer happens by the movement of ions through molten electrolytes in the solution of electrolyte. Okay. So an ionic compounds are made up of charged ions. They can conduct electricity, but only if the ions can move. Okay. So here we can see when it is a solid ionic compound, then the ions are very close, so they do not allow the passage of electricity. But when it gets molted or if it is dissolved in water, then the ions become far apart from each other and they allow passage of current. What is the difference between electronic conductor and electrolytic conductor? So electronic conductor allows flow of electricity by direct flow of electrons through the conductors, while electrolytic conductors allows electron transfer by the migration of ions. So here the electricity is conducted by flow of electrons, while in electrolytic conductors the electricity is conducted by the flow of or migration of ions. Here in electronic conductors, the conduction does not involve transfer of matter. It is only flow of electrons. While here in electrolytic conduction involves the transfer of matter. So electronic conductor is no chemical change, while here in electrolytic conductor the chemical change happens. Okay. Now resistance of conductor increases and conductivity decreases by an increase in temperature. So when you are increasing temperature, the resistance of the conductor increases, but the conductivity decreases. While here in electrolytic conductors, when resistance of the conductor decreases and conductivity increases by increase of temperature. Okay. Then conductance of metallic conductor is very high, while conductance of electrolytic conductor is comparatively low. So, example for the electronic conductors are solid or molten metals such as aluminium, copper, while here it is solution of NaCl, acetic acid, etc. Solution of acids, aqueous solution of acids. Okay. Then electrolytes. Compounds that conduct electricity in the molten or in aqueous solution are called electrolytes. Now, electrolytes are of two types, strong electrolytes and weak electrolytes. Strong electrolytes are the ones which dissociate completely into their ions in the aqueous solution. So, conductivity is very high in these because the more ions are available. While in weak electrolytes, the electrolytes dissociate to a small extent in aqueous solution, and hence they show lower conductivity. Here the example is strong acids and bases, while here example is weak acids and bases. Clear? Okay. So here this is ethanol. Ethanol, there is no ions, no conductivity because there is no dissociation of ions, hence they are non-conducting. Next is KCl. KCl is dissociated completely. It's a strong electrolyte, and therefore it will be there will be dissociation to form ions, complete dissociation. So hence the conductivity will be high. Third example is acetic acid. Acetic acid is a weak acid. It is a weak electrolyte. It partially dissociates, so shows low conductivity. Okay. So hence electrochemistry is a study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about the non-spontaneous chemical transformations. So here, when the chemical reaction takes place, during that chemical reaction, the electricity, there is flow of electrons and the electricity is produced. So we study about those cells, and then also we study about the cells where you provide electrical energy and then only the chemical transformation occurs. So in the first case, it is a spontaneous chemical reaction that brings about production of electricity, while in the second case, electrical energy helps to undergo a non-spontaneous chemical transformation. Okay. So electrochemical cells. So there are two types of electrochemical cells. Are the two types of electrochemical cells. One is galvanic cell. It is a cell which electricity is produced by a spontaneous reaction. For example, Denier cell. While electrolytic cells are the devices to carry out non-spontaneous chemical reactions using electricity. So you have to give electricity from outside, then only the non-spontaneous chemical reactions takes place. Okay. Now this is galvanic cell. You see here two beakers are given. In one beaker zinc anode is dipped in zinc sulfate solution. In another beaker copper is dipped in copper sulfate solution. And these two are connected to a voltmeter. Okay. And then these two solutions are connected also by a inverted U tube which contains potassium chloride inert electrolyte, and this is called salt bridge. So basically when you dip zinc rod in zinc sulfate solution, what happens? The spontaneous redox reaction takes place. Now let's see how. When your zinc rod is dipped in zinc sulfate solution, the zinc loses its electron and it converts to zinc ion. So zinc is oxidized to zinc ion at anode. So at anode, what reaction is happening? Oxidation reaction is taking place. Okay. Now here in what do you see? There are copper ions in the solution. The copper ions takes these electrons that were released in zinc, flow from zinc to copper, and copper ions from the solution gains electron and deposits in the form of copper on the copper rod. Okay. So the reduction takes place here. Copper ions, they gain electrons and they convert to copper, and so the net reaction is what? Zinc converts to zinc ion, copper ions convert to copper. So zinc plus copper ions gives you zinc ions plus copper. So this is the net reaction and this is a redox reaction, because in this reduction and oxidation is happening simultaneously. So the electrons, they flow from zinc to copper and the current flows from copper to zinc. So copper ions gained electron, they converted to copper. Zinc loses electron, converts to zinc, and this is a oxidation half reaction. So the net reaction is what? Zinc plus copper ions gives you zinc ions plus copper. So in a galvanic cell, the half cell in which oxidation takes place is called anode, and it has got a negative potential with respect to the solution. The other half cell is reduction takes place is called cathode, and it has got a positive potential with respect to solution. So now what is potential? That means a potential difference develops between the electrode and electrolyte, which is called electrode potential. How does it develop? When you dip metal in metal solution, the electrode potential develops. So when the concentration of all the species involved in half cell is unity, then the electrode potential is called standard electrode potential, which is measured in standard conditions. There is 1 atmospheric pressure and 25° centigrade temperature. So according to the IUPAC convention, standard reduction potentials are called redox potentials. Cell potential. So the potential developed between the two electrodes of galvanic cell is called cell potential, and it is measured in volts. So cell potential is the difference between the reduction potentials of cathode and anode, and it is called the electromotive force. So what is electromotive force? It is the difference in electrode potentials. Which potentials? Reduction potentials of cathode and anode of the cell. So my formula is what? The EMF of the cell is positive and is given by the potential of the half cell on the right minus half cell on the left. So E cell equals to E right minus E left. How do you represent a cell? Always the anode is kept to the left and cathode is kept to the right. In anode, metal is represented by first followed by metal ion. Then in cathode, metal ion is represented first followed by metal. Put a vertical line between metal and metal ion. Put a double vertical line between the two electrodes. So cell reaction, copper plus 2 silver. Let's see this cell. Silver ions plus gives you copper ions plus 2 silver. So this is half cell reaction will be what? Here, which is what is undergoing oxidation, which is undergoing reduction. At cathode, the reduction is happening and silver ions gain electron to convert to silver, and copper loses electrons and converts to copper ion plus 2 electron. Now how do you represent this cell? Which is anode here. Anode is copper. So first we write the metal, then separate with vertical line, then metal ion, separate by double vertical line, which indicates the salt bridge. Then silver ions are the cathode metallic ions separated by a line, and silver solid. So copper 2 plus silver ions and silver. Which is anode here? Anode is copper ions. Which is cathode here? Silver ions and silver. Now how do we find out the standard redox potential? We must compare the half reactions to a standard. What is that? For example, here you see 2H plus 2 electrons gives you H2 plus 2 H2O. So here in this cell, the electrode potential is 0, and this is called standard hydrogen electrode. And we have a standard, we can calculate the redox potential by using the table of standard reduction potential. Now you see the structure of the standard hydrogen electrode. Here you see there is a beaker which contains 1 mScl. Then there is this glass tube, which is having an opening through which hydrogen gas is passed. In the center of it, there is a platinum wire, and on the top of it, it is a platinized plate, which is called platinum electrode. This setup is dipped in the beaker containing 1 mScl. So hydrogen gas at 1 atmosphere is bubbled into it, and this is a standard hydrogen electrode. So this standard reduction potential is the voltage associated with the reduction reactions at an electrode when all solutes are 1 m and all gases are at 1 atmospheric pressure. So we use basically the standard hydrogen electrode to calculate the standard reduction potentials of the various half cells, various electrodes. So this is the reduction reaction. This standard hydrogen electrode can act as a cathode also and also as an anode depending on the reduction potential of the second electrode. So if that means this can undergo reduction also and this can undergo oxidation also. So if it is connected to the electrode which is having a lower reduction potential, then this will undergo reduction. But when it is connected to another electrode which is having a less higher electrode potential, then this acts as a anode. So if it acts as a cathode, then the reaction would be 2H plus 2 electron gives you hydrogen at 1 atmosphere. So E naught is 0. Then if you are connecting it to the electrode which is having a lesser electrode potential than 0, then this acts as a cathode and this acts as an anode. So we have taken zinc sulfate and hydrogen electrode, connected the hydrogen electrode and zinc to the voltmeter, connected the two solutions zinc sulfate and 1 mScl through a salt bridge. Okay, so what will happen at zinc anode Zinc is anode, so the zinc ions separated by salt bridge H plus and H2, and this is comma platinum. Platinum is the electrode here. Okay, so in this zinc undergoes oxidation reaction. Okay, zinc ions are formed. Zinc gives you zinc ions plus 2 electron, and cathode reaction will be H plus 2 electrons gives you hydrogen. So hydrogen gas is evolved at cathode. Now my net reaction will be what? Zinc plus 2H plus gives you zinc ions plus hydrogen. So, okay. Standard EMF, how will you calculate? My formula for the standard EMF is E naught cell is equal to E naught cathode minus E naught anode. So, the E naught hydrogen minus hydrogen ions hydrogen gives you minus E naught zinc ion zinc. So H plus into H2, this is a reduction reaction. That means we require to write the reduction potential here. Then E naught zinc ion zinc, this is also reduction reaction. So we require to write the reduction potentials for both of them. Where the reduction is happening at cathode, that is with the hydrogen electrode, and where is the oxidation happening with the anode, that is zinc. What are the values? Now let's see. The value for hydrogen is 0 and the value that comes in the voltmeter is 0.76 volts. So you can calculate the standard hydrogen standard potential for standard reduction potential for zinc. Okay. So that is equal to minus 0.76 volts. So basically this SHE, She, that is a standard hydrogen electrode, is used to calculate the electrode potential of various half cells, various electrodes. Now, so zinc ions plus 2 electrons gives you zinc. Okay. Now, if you connect this hydrogen electrode to the copper electrode, then copper half cell, then what will happen? Here on the left side, you are having hydrogen electrode dipped in 1 amp, so as SCl, and on this side, you are having copper dipped in copper sulfate solution 1 amp. Both are 1 amp. Now, these two are connected by salt bridge, and this is connected through wires to a voltmeter. Okay. Now, what happens at what is the how do you represent the cell? Platinum, hydrogen, 1 atmosphere, then H plus separated by a vertical line, H plus 1 m, separated by a double vertical line, copper 2 plus 1 m, and the copper solid. Okay. Now, which is anode here? Anode is a hydrogen electrode. So this undergoes oxidation, and H2 gives you 2H plus 2 electrons. And cathode undergoes reduction. So copper ions gain 2 electrons gives you copper solid. So what is my net reaction? And net reaction is H2 plus Cu2 plus gives you Cu plus 2H plus. Okay. Okay. So what is how we will calculate the E naught cell? E naught cell equal to E naught cathode minus E naught anode. Here you know the electrode potential of the cell. You come to know from this the value that comes here. And E naught cathode, you know it's 0. So you can calculate E naught anode. That is the electrode potential of the E naught cathode you don't know, E naught anode you know, and you know E naught cell. So E naught cell is 0.34, E naught cathode is unknown, and E naught anode is 0. So you can calculate E naught cathode 0.34 volts. Now this is the electrochemical series in which the standard reduction potentials of the various cells are given. Half reactions are given for various electrodes. So you see this is in the order of decreasing standard reduction potential. So one which is on the top will undergo reduction easily because it is having a positive value, higher value of the reduction potential. One which is below is having a very low value of the reduction potential. That means this will undergo oxidation. So they will be strong reducing agents while this will be strong oxidizing agents. They undergo reduction, so they are strong oxidizing agent. So in this table, it is written on the basis of increasing standard oxidation potential but decreasing standard reduction potential. Okay. So here the highest reduction potential is of the fluorine and lowest is of the lithium. Okay. Then so E naught is a reaction. E naught for the reaction is written as E naught. standard reduction potential is written as E naught. The more positive standard reduction potential, the greater is the tendency to get reduced. Half cell reactions are reversible. That means the sign of E naught changes when the reaction is reversed. So if the reaction is written as a reduction reaction and its electrode potential is plus, then if it is written as a reversible reaction, that means oxidation reaction, the sign will get reversed. The value will remain same, but the sign will get reversed. So changing the sign, stoichiometric coefficient uh, setting of the cell. Half cell with lower standard electrode potential is taken as anode, and that higher value is taken as cathode. Okay. So if you know the standard reduction potential values, you can make out which is cathode and which is anode. Okay. Now Nernst equation, Mn plus aqueous plus n electrons gives you M. Let us take this in electrode direction. So how will you write the E naught cell? E is equal to, E of the cell is equal to E naught cell minus 2.303 RT by NF log 1 upon Mn plus ion. R here is what? The gas constant, the value is 8.314 joules per Kelvin per mole. F is Faraday constant, the value is 96500 approximately coulombs per mole. N is the number of electrons, T is temperature in kelvins, Mn plus is the concentration of the species, Mn plus. Okay. Now for the Daniell cell, E naught, the one which we saw just now, E naught, E copper ions copper is equal to E naught copper ions copper minus 2.303 RT by NF. The electrons transferred are 2. So instead of N we can write 2, and 2F is equal to log 1 upon copper ions. Okay. Then if it's zinc electrode, how will you write? E zinc ion zinc gives you E naught zinc ion zinc minus 2.303 RT by 2F log 1 upon zinc. Okay. Now you know E cell equals to E naught cathode minus E naught anode. Yeah. So it will be copper minus zinc. So this equation minus this, it will give you, take 2.30, it will give you E naught copper ions copper, E naught zinc ions zinc minus 2.323 RT by 2F if we make it common log zinc upon copper. So E naught cell, this is cathode minus anode. So this is E naught cell minus 2.30 RT by 2F log zinc ions upon copper ions. So E naught cell minus, if you divide 2.303 RT by 2F. So this 2.303 RT by F is equal to 0.059. Okay. And 0.059 upon 2 is what? 0.0295. So 2.303 RT by F comes out to be 0.059. This divided by 2 will give you 0.0295 log zinc ions upon copper ions. So this is the Nernst equation for Daniell cell. It can be seen that E cell increases with increase in concentration of copper and decreases with increase in concentration of zinc. Is that clear? Okay, thank you. Now, if A gets oxidized, it loses electron and the reaction is called oxidation. If sodium gets oxidized, it loses electron, it changes to sodium ion. So when you see sodium ion here, for sodium the oxidation number is 0, but for sodium plus it is plus 1. So the oxidation number is increasing, therefore the oxidation number is increasing, therefore it is an oxidation reaction. Now B plus, if it gains electron, it changes it to a reduced state, the oxidation number decreases. So zinc loses, zinc ions gain electron and convert to zinc. This is a reduced state. So oxidation number decreases from +2 to 0. Now if A and B combine, the electron flows from the oxidized state to the reduced state. This flow of electric current is called conduction. So oxidation is loss of electron, reduction is gain of electron. Okay, so gain of electron is called reduction and loss of electron is called oxidation. Electrons flows from oxidation half to reduction half. Now these some reactions are given. Just check out which is the oxidation half reaction and which is the reduction half reaction. So Fe2 plus is changing to Fe3 plus plus electron. So it is losing electron, the loss of electron. Therefore it is what reaction? What reaction? Oxidation. Aluminium gains electron, converts to aluminium. What reaction? Reduction. Water gains electron, converts to H2NOH. Which reaction? Reduction. Manganese converts to manganese reacts with water to form manganese dioxide 4H plus and 2 electron. Loss of electron. So it is oxidation. First one oxidation, second one reduction, third one reduction, fourth one oxidation. So when metal plate is dipped in its salt solution, what happens? Either the electrons are removed or electrons are gained. When it is loss of electron, you call it as de-electronation. When it is gain of electron, you call it as electronation. So when the tendency of the metal is atom to go into the solution, leaving the electrons on the metal plate is higher, then it is called de-electronation. But when the tendency of the ions in the solution to deposit on the metal plate by removing electron is higher, then it is electronation. Okay. So de-electronation and electronation. So the electrode potential is the difference of electrode potential is the difference of electrode potential between the metal electrode and its solution in equilibrium conditions. Yeah. So when you dip metal rod in metal solution, either the electrons are removed or the electrons are gained. So when the electrons are removed, what happens? Then there is a negative charge on the plate and the positive charge around, because the electron, it was earlier zinc, it has lost electrons to the plate. So electrons are there in the plate and outside there is a positive charge. So this is a oxidation half. While if the ions from the solution gain electron and convert to a neutral atom, so there is a positive charge developed here on the metal plate and negative charge around it. So this is for the anode and this is for the cathode. So here forward reaction faster than backward and forward reaction slower than backward. So cell potential is basically equal to E naught of anode minus plus E naught cathode. Okay. So standard cell potential is the potential of the galvanic cell when all the substances involved in the cell reaction are in the standard states at 1 m concentration, gases at 1 m, 1 atmospheric pressure, solids and liquids are in pure state with all at 25 degrees centigrade. Then you call the EMF as standard EMF. And the formula is E naught oxidation of anode plus E naught reduction of cathode. So the standard cell potential is basically the, according to IUPAC, it is given, it is E naught cell is, for that you require to take the reduction potentials of both. So E naught cathode and minus E naught anode. So the right hand side electrode minus the left hand side electrode, their potentials gives you the standard cell potential. Okay. So the Nernst equation that we did earlier, the cell potential and the electrode potential, they depend on temperature, concentration of solute and the partial pressure of the gases. So this dependence of potential is given by Nernst equation. E is equal to E naught minus RTNF ln Q, where Q is what? The reaction coefficient. So Q is equal to products and reactants. Okay. Then E is equal to E naught minus RT by NF ln products upon reactants. E is equal to E naught minus 2.303 RT by NF log to the base 10 products upon reactants. So this is my formula. So E is equal to En 2.303 RT by F. If you put the values, it comes to 0.059 upon N log to the base 10 products upon reactants. Now how you calculate the Gibbs free energy? Gibbs free energy is a useful work done by a system. So here the useful work is the electrical work done by the galvanic cell. And electrical work is given by NF into E, charge into cell potential, CV. Okay. So NFE. Reversible electrical work done in the galvanic cell is due to the decrease in free energy. So electrical work is equal to minus delta G. Okay. Minus delta G is equal to NFE cell, E naught cell. So this is equal to delta G is equal to minus NFE naught cell. E naught is equal to delta G naught upon NF. So delta G naught is nothing else but Gibbs free energy change. Now delta G naught is equal to minus NFE naught cell, and delta G naught is also equal to minus RT ln K. So we can find the relationship between standard cell potential and the equilibrium constant. What is K? Equilibrium constant. So combining the two equations, it is NF minus NFE naught equals to minus RT ln K. Okay. Now E naught is equal to RT by 2 NF ln K. Okay. RT by NF ln K. So E naught cell equals to. So this RT, put the value, convert this ln to log to the base 10, multiply with 2.303. RT by NF log to the base 10K. Okay. Putting the value of RT and F, you get 0.059 upon N log to the base 10K at 25 degrees centigrade. Now how will you represent the half cell? Copper metal dipped in copper chloride, nickel metal dipped in nickel sulfate, magnesium dipped in magnesium chloride 0.01 m, hydrogen gas of 1 atmosphere passed through solution of hydrochloric acid of 1 m.